D is equal to epsilon E, where d bar is referred to as displacement density or electric flux density. So what do we understand when we say electric flux density? Like line charge density, which is charge per unit length, or surface charge density, charge per unit area, or volume charge density, charge per unit volume. Electric flux density is number of electric lines of flux passing through a unit normal area. So if you know the number of electric lines of flux passing through a unit normal area, then you know the electric flux density. Any surface is mathematically modeled in terms of a vector, say ts bar or a bar, which is perpendicular to that surface. Area is always modeled as a vector perpendicular to this surface. So that's the reason whenever we define an area, we refer it to as a normal area. Now what is this electric lines of flux passing through a unit normal area? So before we understand the electric flux or the definition of electric flux density, let's recall the concept of positive and negative electric charges in electric field. As we know, the source of electric field is a charge, and the charge can be a positive charge or a negative charge. The basic property of a positive charge is electric lines of flux emerge from this charge. Right? And negative charge is that charge where electric lines of flux terminate. So basically, one acts like a source, the other acts like a sink. So this is a source and this is a sink. There are sources and sinks present in the electric field. That is the reason when you consider a positive charge and a positive charge placed side by side, say Q1 and Q2, so the force of repulsion between these two charges exists. So we talk about the repulsive force between the two charges, and we say they move away from each other. Positive charges repel. When there is a positive charge and a negative charge, there is an attractive force between these two charges. We say charges attract. That means they move towards each other. That's because of the basic property of these two charges, positive charges and negative charges. So there exist sources and sinks in electric field, which is unique only to electric field. As we will see for magnetic field's case, there exists no concept of positive magnetic charges or negative magnetic charges. So this property is unique to electric fields. That means when you have a closed surface S, and if I say there is some electric charge Q present on the surface, then there will be some lines of flux. The field can be interpreted in terms of some lines of flux emerging from the surface. So these lines of flux that emerge from the surface, they try to terminate on a negative charge. Okay, so these lines of flux that emerge from the surface surrounded by electric charge Q is nothing but the field. Is nothing but the electric field in the vicinity of this charge. So in order to understand the effect of the charge in its vicinity, we interpret the field in terms of some lines of flux. Don't think that there is some gap between these lines. Okay, so this is a physical interpretation, and do not mistake it as some gap between the lines, or what should be the distance between the lines, and what will happen if these lines are far away or they are close to each other. So this is just a diagrammatic representation of the lines of flux, and need not worry about the distance, or you will not find such kind of distance between these lines of flux. So we are interpreting the field in terms of some lines of flux emerging from it. So to understand the effect of the field produced by this charge, we take the help of these lines of flux. So you could say that in some way electric lines of flux are related to electric lines of field, even though there is a slight difference between these two terms, electric lines of field, electric lines of flux. But for simplicity, we can consider that both of them are equivalent. So coming back to the electric flux density, it says that number of electric lines of flux passing through a unit normal area. So if you have a closed surface S surrounded by electric charge Q, and if you take a small surface of area unity of area as 1 unit, we know this small surface can be represented by a vector which is perpendicular to this surface, say ds bar. So this ds bar is a vector which represents this small surface, and the area of this small surface is 1 unit. That means mod ds bar is equal to 1. So even in this case, this small surface of area unity, there would be some lines of flux emerging from the surface, and if you know the number of electric lines of flux passing through this unit normal area, that means you know electric flux density d bar. Okay, so like I said in the previous class, d bar is referred to as displacement density or electric flux density. So we may sometimes call it as displacement density, or sometimes refer to as electric flux density. Many times in the literature you will hear this terminology, because this terminology is quite popular as we talk about the Gauss law in our next topic, because we will use Gauss law many times in field theory. So this terminology of electric flux density also will be used frequently in field theory. But do remember that this is not different from displacement density, and both of them are the same. So I could call it as electric flux density or displacement density, or I could talk about electric flux or displacement. They are equivalent to each other. Okay. Now, what is Gauss law? State Gauss law. If you are unable to state Gauss law, let's do it this way. Let's start with a closed surface S surrounded by an electric charge Q. The moment I say there is an electric charge Q in the surface, we can interpret this with some lines of flux emerging from the surface. Right? Let us consider a small surface ds represented by a vector perpendicular to this surface. As a mathematical representation of this surface, small surface of area ds. This ds is a scalar. Ds bar is a vector, and the relation between ds bar and this ds is mod ds bar is equal to ds. Now say you know the number of electric lines of flux passing through a unit normal area. That means you know d bar for this case. So if you have a small area, a small surface of area unity, say you know how many lines of flux are emerging from this small surface of area unity. You made some measurements and you found out d bar. Okay. Now, can you tell me what would be the electric flux linking the small surface at ds? Write down what is d phi. What is electric flux linking this small surface ds? What do you understand by this statement? Electric flux linking the small surface ds. That means if you know number of electric lines of flux passing through a unit normal area, now the question is what is the number of electric lines of flux that pass through a small surface of area ds? That is what we mean by electric flux linking this small surface ds. How do you find out? You know electric flux density, you know ds bar, that is a vector which represents the area ds. So electric flux can be found out as d bar dot ds bar. You can't multiply d bar and ds bar because they are vectors. Multiplication of vectors means taking the dot product or cross product. Now you see, verify. D bar is electric flux density. Electric flux by area. Area gets cancelled. You will get electric flux. That's correct. And electric flux is a scalar quantity. Perfect. Now if you know number of electric lines of flux passing through a small surface of area ds, what would be the electric flux linking the whole surface S? What would be the electric flux linking the whole surface S? What do you mean by this statement? Now we are interested in finding out what is the number of electric lines of flux that emerge from the whole surface S surrounded by electric charge Q. Of course, it is difficult to find out the value just by using mathematical interpretation. So the result would be based on the result from various experiments, but mathematically how will you calculate this? Mathematically you can calculate the electric flux linking the surface S, or the number of lines of flux passing through this surface S surrounded by electric charge Q, as take the surface integral of d bar dot ds. It's fine. So mathematically we can find out the total electric flux linking the surfaces as surface integral d dot ds. Then what is Gauss law? Gauss experimentally proved that this is equal to the amount of charge enclosed by the surface. So the total electric flux linking the closed surface S surrounded by electric charge Q is equal to the amount of charge enclosed by the surface. What does it mean? Number of electric lines of flux passing through a surface S surrounded by electric charge Q is equal to Q units of the charge, right? So that means one electric line of flux will correspond to 1 unit of the charge. Look at the interesting result that we got. Important from examination point of view. So if you interpret the field associated with the surface S surrounded by electric charge Q in terms of some lines of flux emerging from the surface, then each line of flux corresponds to 1 unit of the charge.